All right, I believe this is the lecture number 18 in our introduction to statistics, business statistics course, and this is actually one of my favorite topics in the entire course, business statistics, and unfortunately, this is going to be the last topic that is still doable by hand. So far, everything that we've done, actually. All the tests that we performed, all the confidence intervals that we created, all of that could have been done by hand without much, many complicated steps. Now, a lot of that we didn't do by hand. We called certain function, right, in R Studio and test, for example, right. We pretty much called the function either t-test or prop test, and the function created p-value for us. But that p-value could have been computed using pretty simple calculations. This is going to be the last topic where we will be able to do that. Okay. From that point on, everything that we will do in this class will be doable only through the calling the appropriate function through the use of the software. So this is going to be the last topic where we could calculate things by hand pretty easily and get to the answer. Okay, so chi-squared goodness of fit test. So what is that? First thing that we're going to discuss in this lecture is the idea of the multinomial experiment. What's a multinomial experiment? And the Pearson goodness of fit chi-squared test that applies to that. So when we discussed proportions, like in the last lecture, essentially each time when you calculate proportion of certain response out of all collected data, we were dealing with something that was called binomial experiment. What is that? Binomial comes from the word bi, which means two, right? So two-nomial experiment. That means that each time when you repeat the same procedure, there are two possible outcomes, right? So for example, if you remember, a few lectures ago we discussed the results of the exit poll, right? The votes, okay? You ask each person coming out of the voting booth, did you vote for Republican or Democrat? So there is outcome number one and there is outcome number two. One we call randomly success, another randomly we call failure. There is no judgment involved, it's just basically labels that we assign to two possible outcomes, right? Republican, Democrat, that's one. Another problem that we discussed in the homework was about, I believe, the Christmas gifts, right? So how many people give each other Christmas gifts in form of the gift cards, right? Not just some things, goods that they buy, but here's gift card, here's money, buy whatever you want, right? And again, we collected the data and asked people, do you receive or do you give the gift cards? And the answers could be yes, no. In the previous lecture, when we discussed market share of soap after we redesigned the packaging, right? Also, we placed the product in the supermarket and we're interested to find out our market share. That means that out of total counts of bar soaps that were sold, was each bar soap ours or was it not ours? One of our competitors, right? So again, there are only two possible outcomes, right? So each time when each bar of soap is sold, it could be either our soap or not ours, right? With certain probability. Probability is equal to market share, okay? So if I occupy, for example, if my sales represent 20% of the market, then each next bar of soap that's being sold, 20% chance that this is my bar and 80% chance that it's somebody else's competitors, right? So there are two outcomes, success or failure. We just label them, okay? And I perform n experiments, n trials, right? So each time when I sell a bar of soap, that's a trial, right? It can be either mine or not mine. Likelihood of 20% or whatever the market share is versus 80%. Each time when the person comes out from the voting place, it can be either Republican, they cast the vote for Republican, or for the Democrat with certain probability, right? If I ask people, do you give gift cards for Christmas? It's either yes or no with a certain probability, right? But that's binomial experiment. Okay, so what's a multinomial experiment? Multinomial is the trial, again. I try the same thing multiple times, right? And each time I can have more than two outcomes. So instead of by two outcomes, I have multi outcomes. For example, and each outcome, so I can enumerate them from 1 to k. K can be a really big number, right? There is no limit really, and each one of them comes with a certain probability, certain proportion of these responses, right? So, for example, number of cars, okay, in the family. So, certain proportion of people have no cars, right? If I'm living in New York City, for example, there is a good chance that I don't really need a car, right? So, 0 cars can be the answer, or it can be only 1 car in the family, or 2 cars, or 3 cars, or more than 3, right? 4 or more. So therefore, each time when I ask people on the street, how many cars do you have? I can record either 0, 1, 2, 3, or over 3, right? And different probabilities can be assigned to these responses, right? Certain proportion of people with no car, families with only 1 car, with 2 cars, 3 cars, or more than 3 cars. So that's an example of the multinomial experiment. Obviously, since k is the total number of possibilities, right? Then if I add together the corresponding probabilities, that should give me certainty, 100%, right? Because I don't know which one of these outcomes will happen. All I know is one of them will happen for sure. So if I add probabilities of all possible outcomes, I should get 100% chance, 1.0, okay? So, and note also that if k equals 2, number of categories equals 2, then I'm back to my binomial experiment, right? So instead of all these different values, that's what I have. 2 different outcomes, and their probabilities should add up to 1, right? So there are people who are voting, and it's either Republican or Democrat, but both of them, that will give me 100% chance, right? Or people either get the gift cards or don't get the gift cards for Christmas, but these are only 2 possibilities. So if I add their probabilities, it should give me 100%. Okay, so k equals 2, my multinomial becomes binomial. All right, so well, here's another example, right? What I just was discussing. 13.5% of people do not have a car, 0 cars, right? 33.7 have only 1 car in the family, 33.5 2 cars, and 19.3 3 or more cars, and these numbers, they should add up to 100%. Okay, so each time when I ask somebody how many cars do you have in the family, the response is assigned to one of these different categories. So multinomial experiment. Okay, so here is the hypothesis that we have tested back then when we discussed one population, right? Can't remember right now what. Oh yeah, the example that we discussed was. Well, we constructed the confidence interval about the voting procedure, right? Is the percentage of people who voted for Republican above 50% or not? Now I remember. The example that we considered for the hypothesis testing was customer satisfaction survey for State Farm insurance, right? So State Farm claims that the proportion of people who are satisfied with service is at least 90%. So that means 90 or more. So the fraction, the proportion is 0.9 or above, right? So if we're skeptical about that, we can collect our own sample, ask people, are you okay with their service or not? Record yes and no responses, and after that we can calculate the point estimate, right? P hat, the proportion from the sample, and we can test hypothesis. And hypothesis testing were one of these 3 different forms, right? One form is proportion in the population. That should be actually, let me change that. Alright, the population proportion is equal to a number or not equal, greater than a number or less than a number, less than or equal to a number, or greater than a number, right? That's what I was testing. I was testing only one proportion for the population, okay? So now I have a more complicated case because there are k different possibilities, right? In general, k can be any number, right? Then how do I test hypothesis when I have more than one possible outcome and therefore more than one proportion? So I cannot really record and test hypothesis in this form, right? There is more than one possibility, so I'm not testing just one proportion, I'm testing many of them, okay? So, and that's where we're going to actually use the chi-square test. So I'm going to, in the next 40 minutes or so, to explain to you how exactly do we deal with the case when you have one population, so there is only one column of data, okay? And we're testing to see if the distribution of responses follows a certain pattern, okay, that we're going to hypothesize. So, chi-squared goodness of fit test, ladies and gentlemen. All right, two companies, A and B. Each one of them is the manufacturer of the fabric softener, okay? So something that you add to your laundry for that to become, you know, soft, I guess, right? A and B, major companies, recently conducted both aggressive advertising to maintain and possibly increase their market share. So again, this is a marketing example, right? Before the campaign, according to the sales generated by retailers, right? Company A product was responsible for about 45% of the market share. Company B was comparable, a little smaller, 40% of the market. And the rest, 15% of the market, was distributed among smaller players, not that well known, not big brand names. It's like, for example, I don't know, detergent, right? What are the big names? Well, Tide is a big name, right? And then there are probably detergents that are manufactured by Costco, you know, a lot of small companies, so they don't have a brand, they don't have a name that stands out, and they're probably responsible for less percentage of sales, right? Okay, so this was the distribution of the market share between the players, right? 45 company A, 40% B, and 15 smaller players. To find out if these market shares changed, they still hold after the advertising campaign, or maybe they were redistributed between the players in the market. Okay? A marketing analyst solicited the preferences from 200 randomly selected customers. So quite simply, they approached 200 people and said, hey, if you're buying fabric softener, which brand do you buy? Is it company A, is it company B, or is it something else? So responses were recorded as, well, let's actually take a look. I can't remember right now, quite frankly, what the responses look like. So let me see. Here's my data. Fabric softener. Alright, so responses are recorded just like the question is asked, right? Which company do you prefer? Some people prefer A, some people prefer B. Some people say it's neither A or B, it's something else, right? Okay, cool. So that's how responses look like. Company A, company B, or other. Here is the big fat question that we have to answer at the end of today's lecture. Can the analyst infer, using 5% significance level, that customer preferences have changed after the advertising campaign? Okay, so let's go ahead and get started with hypothesis. Okay, so our null hypothesis that we're going to test now. Notice again that I'm not asking the question, did company A keep 45% of their market, or did it change, became something else? Or did company B kept 40% of the market, or did that change, right? It became higher, lower, what? I actually need to kind of evaluate the state of the market altogether, right? So my null hypothesis always is going to be like this. Nothing happened, okay? So after advertising was performed, company A, that's my first response, still maintains 45%. Company B still maintains 40%, and other smaller companies, 15% of people still said that they prefer company, not A, not B, but something else, other. Okay, so my null hypothesis basically says that the proportions of responses did not change. So market distribution market allocation is still the same as it was before the advertising, right? So nothing happened really. There was no redistribution of the market share, okay? And my alternative obviously should be opposite of null, right? So in other words, my alternative will read like this: at least one of the proportions, either P1 or P2 or P3 or any combination of them, right, is different from the value that it had before. That's kind of my general way to say that now it's either P1, company A, market share is not 45% but something else, and or company B, P2, market share is not 40% and or P3 is not 15%. So for all I know, all three proportions can change, right? So my company A can control now 35%, company B can control now 50%, and other companies can control, I don't know, 9%, right? So as long as they adapt to 100. So all three can change, or only two can change, or only one. Well, one cannot change, right? If one changed, that means something else also changed. But at least one proportion is not equal to its previous value. So this is kind of my generic way to write down the statement that market shares are not the same after the advertising as they were before. Okay. All right. So let's get cracking. Now, as I was telling you many times already, we always start hypothesis testing by believing that the null hypothesis is true. So we believe that this statement is the case, right? The proportions of companies, proportion of customers, right, that still prefer company A is still 45%. The proportion of customers that still prefer company B is 40%, and the proportion of people who prefer company C, other, right, not A, not B or something else, is 15%. Okay, so first of all, well, let's actually start with our code. Okay, so how do I name my data frame, data set? Softener, okay, or fabric softener data. Okay, and it comes from the file, CSV file, which I again put in C data, and it's called, if I remember correctly, fabric softener.csv. Let's see, yeah, that's true. Okay, so let's take a look at the structure. Okay, structure of the fabric softener data. All right, there you go. I can see that my data contains 200 customers, right? 200 observations, we knew that, and only one column. So I'm actually back to testing one population. Let's go back to the analysis flowchart, right? I told you that pretty much we're going to use that flowchart in every lecture. This is our map of the course, right? Every test that we're going to be doing should fit somewhere on this flowchart. So I'm describing a population, right? I'm dealing with a single population, right? People responding to my question, which fabric softener do you prefer, A, B, or something else? Data are nominal, obviously, right? Because there is they're not numerical, that's for sure. They're not numbers, right? And they're not ordinal because there is no order between A, B, or other. It's just basically three different answers. One is not better than another. Okay. Number of categories. If I have two categories, such as Republican, Democrat, or I do receive gift cards, or I do not receive gift cards, then I have to use z-test to test for the proportion. Okay. But in my case, I have three categories, right? Company A, company B, or other. So therefore, I have to use the chi-squared goodness-of-fit test. So this is an example how you should be using this flow chart to find your way through the maze of a lot of different tests that we already covered, and we will actually still cover. Still have about half of the course in front of us, right? We'll still discuss in the rest of the semester. Okay, so I know that here for this problem I have to use chi-squared goodness-of-fit. Okay, so here's the idea for the chi-squared goodness-of-fit. Let me first of all calculate. So I'm gonna type here. Okay, we start by believing that null H0 is true. Okay, now what does that mean? That means that 45%, if null was perfectly true, then 45% of customers will still buy company A, right? And I know that my number of records, again, it's a good practice, right? N row, number of records, whoops, N row in my data set, which is fabric softener data. I'm going to say N equals what? N is equal to 100, okay? So 45% of people, if null is true, and I start by believing that the null is true, then 45% of people will say that they still buy company A, right? So I expect, I'm going to use letter E, expected number of responses for the category number 1, fabric softener for company A, should be N 200 times 45%, right? So if I type it out, E1 is, whoopsie, something went wrong. Okay, E1 is 90. Okay, so 45% of 200 people, 200 times 45, 90, right? So if null was perfectly true, and 45% of people would still prefer company A, 90 of them will say, I still prefer company A. That's what I expect. That's why I have E right here, okay? So now, second category, company B, E2. Before the market, before the advertising, 40% people preferred company B, right? So if null is still true and 40% still prefer company B, then 40% of 200 people, or 80, right? Let's see, E2 is 80. 80 people in my sample would say that they still like company B. And 15%, let me call it E3, expected number for the response number 3, out of N 200, 15% would say I still prefer not A, not B, but other. So E3 must be what? 15% of 200, that's 30, right? Yeah, that's 30. So 90 plus 80 plus 30 gives you 200, right? That's everybody. That's what I expect to see if null was perfectly true. And no market share changes happened after the aggressive advertising campaign. But of course, the reality is a little bit different, right? So let's see how actually my responses were distributed. So I'm going to tabulate my, so I'm going to call it actual responses, right? Responses is a result of the table function, and that would be coming from fabric softener data $softener. Okay, that's the only column that I have. You can see that right here, right? Data frame fabric softener data has one column which is called softener. There you go. Okay, so now let's take a look at the actual responses. All right, so actual responses are like this. And they're alphabetically organized. You know that, right? We discussed that many times. Okay, the way how the responses are listed is in alphabetical order. The categories are listed is in alphabetical order. So C comes first, and A comes before B, right? Therefore, company A is listed 1, company B is listed as 2, and other, because it starts with O, is listed 3rd, right? Okay, so this is my actual frequencies. Right, so I'm going to call F1, which happens to be company A, precisely what I used as my first response here, right? Is going to be my actual response. Actual responses, first element, right? Yeah. So the actual frequency, if you can see it, F1 is 102, right? There. Okay. Now I'm going to do the same thing with the rest of this. So my second actual frequency is the actual response number 2. Alright, that would be 82. And of course, now you know what, programmers should be lazy, so copy paste. The third response is my actual frequency F3, right? Okay, so the first response, if null is perfectly true, should be 90. That's how many people should like still company A if null is perfectly true. In actuality, my survey shows that it's 102, so it's not 90, right? Second response, 80 people, right here, 80 people should still prefer company B, and 82 people in my sample in actuality liked company B. That's not very different, right? So it's pretty close. And 30 people should prefer others, not A, not B, but something else, some other manufacturer, if null would be perfectly true, while in actuality only half of them, 16, right, answered that they would go with other providers. So let's now discuss, is that an indication that my null is not true, or is it not? How do we judge? Well, here is what the test does. Okay, here's how chi-square test works. If my null would be perfectly fine, would be perfectly true, then this is what I expect to be in the file if null is true, and that's what I would observe, right? So if that count is 90, that count is 80, and that count is 30, then I would say, wow, look at that. My expected values, if null is true, are exactly the same values as what I see in the file. What does that mean? That means that the null is true, right? So if my expected frequencies are equal to the actual frequencies, so these numbers E1, E2, and E3 are equal to F1, F2, and F3, what I expect to see if the null is true and what I actually see from the data, if they are the same exactly, then I would have just plain and simple null is true, no question about that, right? But as you can see, there are differences. 90 is what I would expect to see about company A if null was true, but in actuality it's not. It's something else, right? And the bigger these differences are between 90 and 102, 80 and 82, 30 and 16 in our specific example, the more evidence I have to support my alternative, right? My actual counts that would be true if null would be the case, they deviate from the expected counts, right? What I would expect to see if null was completely true. So the bigger differences I observe between the expected and actual frequencies, the more evidence I have to support my alternative hypothesis, right? The bigger the deviations, the more it speaks towards my alternative hypothesis. So here's how the test is done. Let's go back to the slides. And on these slides I basically explain exactly what we were doing. Okay, so this is what we when we calculate the actual frequencies of responses, 102, 82, 16, etc. Okay, so the test is performed like this. We have to construct this ugly creature. Okay, statisticians showed that if you create this construct, okay, if you use your expected frequencies and actual frequencies like this, calculate the difference, square that, and divide by expected frequency, and add them together across all categories. We have three categories, right? Three possible answers: company A, company B, or other. Then you'll get something. You'll get a number, right? And this number for different samples, it was shown, is distributed according to the chi-squared distribution. Okay, so it's not X, it's a Greek letter chi. And let me show you how the chi-squared distribution looks like. So what I found is, actually it's the same website that I used before once to demonstrate. I believe I demonstrated t-distribution or something like this. Or maybe it's not sampling distribution, it was something else. I can't remember right now. So chi-squared. So this is what chi-squared looks like. Okay. Note that unlike two other distributions that we looked at, t and normal distribution, both t and normal, they go to the minus infinity on the left and plus infinity on the right. Chi-squared always starts at it doesn't go below 0. Okay, so it starts at 0 and goes to plus infinity. So, and the only parameter that we need for the chi-squared distribution is, just like for the t-distribution, number of degrees of freedom. Okay, so this is what it looks like when number of degrees of freedom is 1. So let's start increasing number of degrees of freedom 2. Okay, so now let's actually start increasing it right here. What happens if 3 degrees of freedom. Okay, so now it looks like severely skewed. Well, we know that it's severely skewed to the right. But as you can see, as I increase number of degrees of freedom, the skew kind of becomes less and less, right? Still starts at 0, goes to plus infinity, always. And you can see that as I increase number of degrees of freedom, its shape becomes to look more and more like what? What does it look like? Like normal, our good old friend, normal distribution, okay? Yeah, but it never goes below 0. So that's my chi-squared. So let me go back to, I don't know, 3 degrees of freedom, like this. Okay, good. Now let's revert back. So statisticians showed that if I keep getting another sample and another sample and another sample and calculate this number, actual frequencies minus expected squared divided by the expected, add together across all different categories, then the resulting numbers will start forming the chi-square distribution shape. Okay, and since there is only one parameter, number of degrees of freedom, number of degrees of freedom is equal to k minus 1, which is where k is not the sample size. Remember, when we used t distribution, our degrees of freedom number was always sample size minus 1. So if your sample is 50 observations, 50 numbers, and degrees of freedom is 49. If you have 100 observations, it's 99, right? Not the case with chi-squared. For the chi-squared test, number of degrees of freedom, goodness of fit test, is number of categories minus 1. So in our specific case, we have what? We have 3 categories, right? Company A, B, or other. So 3 minus 1 is 2. So in this case, we're going to have to use number of degrees of freedom equals 2. And here is something else, okay? As we discussed, what happens if my frequencies, the actual frequencies, are equal to expected frequencies? Exactly equal. That means that what I expect to see if the null is true is precisely what I see in my sample. And that basically tells me that my null is true. And in this case, if you subtract frequencies minus expected frequencies, that would be 0, right? The difference is 0. All the differences are zeros. You square them, you still get 0, so your chi-squared is 0, right? So if you calculate the value of chi-squared and it is 0 or very low, that actually gives you support for the null hypothesis. But as our expected frequencies and the actual frequencies start to deviate from each other, that means that what you expect to see in the sample, if null is true, is not what you're actually seeing in the sample. That gives you more and more support for the alternative hypothesis, right? So the bigger these differences become, the more evidence you have in your sample that null is not true, and we have to switch to alternative, okay? So, in other words, big values of chi-squared support alternative. Small values of chi-squared support the null, right? And, therefore, here's what we need to do. We need to calculate the chi-squared value for the sample that we got, okay? And after that, we have to calculate the p-value, right? So, how do we calculate the p-value? What is that? Well, p-value, in this case, is going to be all the area in the right tail of the chi-squared distribution, which is cut off by the chi-squared value that we calculate from our sample, okay? So, in other words, when we tested the hypothesis about the population mean, there were 3 forms, right, of hypothesis. Less than a number, greater than a number, not equal to a number. And each time when we calculated p-value, we provided the interpretation of the p-value, right? If you test greater than hypothesis, it's in your right tail. If it's less than hypothesis, it's in your left tail. If it's not equal, it's both right and left tail combined, okay? Here is the difference for you between the t-test and the chi-squared test. For the chi-squared test, goodness of fit, your p-value is always in the right tail of the distribution, because your support for the alternative hypothesis are high values of chi-squared. So the probability to see the sample with that chi-squared or even more, that is your p-value. That basically points towards alternative hypothesis for you, okay? So now let's go back and calculate the chi-squared, right? I have all the frequencies. I have expected, I have the actual. Alright, so I'm going to calculate, and the chi-squared, it's kind of written as chi squared, but it's pronounced as chi-squared, right? Chi squared, chi-squared value for my specific sample, right? Remember the formula, sum of actual minus expected squared divided by expected. So I'm going to do exactly that. I'm going to take first frequency, which is what? This one right here, 102, right? Minus the expected, which is what? 90. F1 minus E1. And I'm going to do that exactly how it's done in Excel. Squared divided by E1, right? That's my first category, company A. I'm going to do the same exact thing for the second one. F2 minus E2. These calculations, by the way, you can do in Excel or even calculator. Doesn't even matter. I'm using R because R, I mean, I can use that just as a calculator like this. Okay, divided by E2. That's my second category, company B. And here's my third frequency, others, minus expected 3 squared, the whole thing squared, divided by the expected value for the others. Alright, so of course I messed up something. Unexpected value, yeah, like this right here, right? See what I did? I forgot to square. Okay, cool. Alright, so let's take a look at how much is my chi-squared value. My chi-squared value is 8.1833. Okay, so it comes from the fact that probably the majority of this chi-squared comes from the fact that company A, I was expecting to see 90, if null was true, but I got 102. That was the difference. B was not that different. I expected 80, and it was 82. And also others, right? That contributed quite a bit. 30 is what I expected to see, but they were 16. So anyhow, that's not 0, right? But is it that different from 0? And how much is the likelihood to see that value of chi-squared, or even more extreme than that, if the null is true? Again, I'm using number of degrees of freedom, df, right? Degrees of freedom, okay, is 2, right? Because I have 3 categories, company A, company B, and other, minus 1, that's 2. Okay, so I need to look in the right tail. Again, p-value is always in the right tail of the chi-squared distribution for the goodness of fit test, okay? Because only high values of chi-squared give me support for the alternative hypothesis, okay? So graphically speaking, let me bring that up, let's see. So degrees of freedom is 2, okay, and oh god, so I have the value of can't really pinpoint that, 8 point something, right? 8.183. I'm gonna try, almost, right? Let me see, I don't remember what was exactly the value. 8.1833. 8.18. I'm trying to adjust it manually. 1833. No, that's too much. I went too far, right? 1. Oh god. That's hard to do. 1833. Almost there. 1835. 1833. Oh, 1835. Okay, good enough. So that essentially is the picture that illustrates my p-value, okay? From the samples, I computed chi-squared value, this weird-looking formula, right? This ugly expression equal to 8.1833, right? And everything to the right from that value, so this area, which is shaded gray, right, in the right tail of the distribution, is probability to see chi-squared like this from a sample, or even more extreme than that, or in other words, even higher than that, right? Because high values of chi-squared give me support for the alternative hypothesis. My p-value is right here. That's the area in my right tail, 0.0167, okay? But that, of course, is not how I want to find my p-value, right? I want to find my p-value by being more precise than just playing with some obscure website, trying to guesstimate, where the position of the the right chi-square is, right? So here's what I'm going to do. Just like before, we used, if you remember, the function to find area in the tail, probability in other words, in the tail of the distribution, we used p-norm, right? Or we used pt for the t distribution. Exactly same thing with chi-squared. I have the function, well, not I, but r, p for chi-squared, CHISQ, chi-squared. So all I have to do is say what is the value that I'm trying to look for, okay? And the value is, of course, this one right here, right? My here, chi-squared value. I actually recorded that, right? Chi-squared value. All right. Now the next one is the only parameter that I have to specify for my chi-squared is degrees of freedom, and I know that degrees of freedom is 2. Or I can simply use that one right here, right? I already recorded that in my variable. So if I say degrees of freedom equals 2, let me leave it 2. I don't want to confuse you any further than you already are confused. And just like in both cases of normal distribution or t-distribution, we have to specify, are we looking in the lower tail or are we looking in the upper tail? So I told you that for the goodness of fit test, we always look in the right tail. So lower tail is false. Simple as that. And there is my p-value, 0.01671. I think actually it's pretty much what I got, right? Where was my website, my beautiful website that I just used? There you go, 0.01671. Yeah, that's the same thing, okay? So graphically, this is what it looks like. Numerically, I got the same answer. Okay, so that is it. So what's the next step? Next step is so now I have the p-value, right? And again, how do I conclude the hypothesis test? I compare the p-value against my significance level. Is it small p-value or is it not so small? What's my significance level? Right here, the problem instructs me to use 5% significance, so standard one, right? Let me switch back to my RStudio, right? So now I'm saying that p-value is 0.01671 and it's less than 0.05. Therefore, reject null hypothesis, right? Sample does give me enough evidence to reject the null hypothesis in favor of alternative H1. And now this is my answer, really, right? But again, this is the answer in statistical language, right? So the way how all the problems, you probably caught up on that already, but let me kind of point that out, okay? Because it feels like it's the right time to do that. So here's how we construct, how we perform the statistical analysis. First, we're getting the business question. Let me show you, okay? So here's my business question. Did market shares change since the advertising campaign, right? So can we, here's the business question, can we infer that the customer preferences have changed after the advertising campaign? That's my business question, right? Step one. Step two, I convert the business question into the hypothesis. This is what this question looks like in the statistical language. So I'm converting the business formulated issue into the statistical language, okay? This is not human, this is statistical language. Null hypothesis, proportion of responses company A is 45, proportion of company B is 40, company 3 is 15, or alternative, at least one is not the same as it was before, right? Then after that I apply the tool, so I do all these steps that we went through, and finally I'm getting the answer. Here is the answer, okay? The tool gives me that the p-value is low, therefore we reject null in favor of alternative. This is the end of problem for statistician, okay? So I got my answer in the statistical terms, but now I have to convert that, translate that back into the human. What does that mean that I reject the null in favor of alternative? Well, let's look. Here's my null. Null basically says that after the advertising, the proportions of the market shares of the products are the same as they were before. That's my null, right? Sample gives me enough evidence to reject the null and claim that at least one market share after the advertising changed, right? So that's my answer in the statistical, in the business terms. That the data gives us evidence that after the advertising campaign by companies A and B, the distribution of the market shares shifted. It's not the same as it was before anymore. Company A, Company B, and other companies, they now control different percentage of the market after the marketing campaign. So this is my answer, again, in human business terms, right? And that's basically how we approached every problem so far. I just didn't tell you that, but essentially we took the problem in business terms, converted that in form of hypothesis, null and alternative, and we used t-test or z-test, or in this case chi-squared test, and we got the answer. P-value less than alpha, reject the null, or is it greater than alpha, fail to reject the null. That's your answer in statistical language. Then convert it into the normal human language after that. Okay. In this case, it means that yes, there was a redistribution of the market shares. Right. Now, what I wanted to point out is this. So, my answer is that the market was redistributed. Right. So where is my answer? Concluding the test right here. Okay. The market was redistributed. That's the end of it. Okay. So, but how exactly it was redistributed? Did company A gain market share and company B gained market share and other companies lost? Or maybe company A gained and company B lost and other companies, they stayed the same? Or could it be that A gained, B didn't move anywhere, and others lost? Or is it B lost and A didn't change really and others gained? This test doesn't answer this question, right? It says that after the campaign, after the advertising campaign, market distribution between the major players is now not the same as it was before. That's it. Okay. So I like to compare the chi-square test to the smoke detector. Smoke detector, basically, when the smoke detector goes out in the house, that means that there is a smoke and possibly there is a fire. Right. That's all it does. Where is the fire exactly? Doesn't say. Right. So and exactly that happens with this test, with the goodness of fit test. And actually, there is another test that we're going to look at very shortly, actually in a couple of lectures. It's called analysis of variances, ANOVA. Exactly same principle. Okay, it indicates that all things are the same or no, they're not. But which things are different doesn't really tell you. That's what ANOVA does. So same thing here. Okay, null says that proportions are the same as they were before. Alternative says no, they're not. The answer that we got out of this hypothesis is no, proportions are not the same. Some are different from what they used to be. But it doesn't tell you exactly what happened, right? Who gained, who lost? Nothing. So this test only tells you if there is a change or is there not a change. Okay, that's it. Okay, so one last thing that I wanted to point out is this. What we did, let me go back to the our code, right? What we did right here, we calculated the expected frequencies and we found the actual frequencies. Then we constructed this ugly looking expression calculating the value of the chi-squared, and then we said, okay, we have to use the chi-square distribution with 2 degrees of freedom and see what area in the right tail is cut off by that calculated chi-squared value. That was the long way to go, right? But we did that manually, and you saw that's why I like this problem. It's actually doable by hand. Okay, so every step of the way you can see what result you get, and the p-value that you calculate, it has very graphical meaning, right? Here is your chi-squared function, here's your value that I compute from the sample, everything to the right is your p-value area under the curve. Okay, and that's what I'm going to ask you to do in the homework as well. But of course there is a shorter way, right? So, and here is how we need to do it, basically. So all of that could be done in one line, quite literally. Okay, so I'm going to receive the same. So if I'm going to get the same p-value, right? Where was my p-value? Let's see. This was my chi-squared test, right? And the p-value was right here. Okay, 0.01671. I don't know, quite frankly, why it types company A for me. So I could do the same. I could get the same p-value by running the function. Okay, so and the function is called chi-square test, right there. Okay, so all these steps can be pretty much smooshed down into one line of code that is packaged nicely, and it will just basically perform the same exact analysis and spit out the answer for us without us doing all these calculations. Okay, and the chi-square test takes several different parameters. Well, actually two of them. Okay, first I need to specify what are my counts. So, and I believe so these are the counts, right? Actual responses. Let me run this again. So actual responses are the counts. Company A goes first. That's important. Okay, company B goes next, and company, well, other, the third response, goes third. Okay, so first I have to send this function chi-squared.test this vector of actual responses, right? So actual, and this is vector, right? Because one variable called actual underscore responses points to three different values. Number 1, 102, number 2, 82, and number 3, 16, right here, right? Okay, and the next one, I have to specify P, I believe, proportions. And because I have three proportions, it has to be a vector. Okay, so reminder, we did that many times. Vectors are created by the function C, combine, right? And how I list the proportions should come from the null hypothesis, which I formulated. And they should be listed in the same order as my different responses are listed in the vector actual responses. So actual responses has company A as the first one, right? And I remember that my hypothesized value for the company A was still 45%, right? Next in my vector actual responses is company B. Company B was 40%. And the last one in actual responses is others, and others proportion hypothesized was still 15%. That's it. So now I run this test, this function chi-squared test, and it tells me that chi-squared value, look at that, it even computed chi-squared value for me right there. Remember, we computed the chi-squared value, the same thing really. Okay, we computed that by hand, and that is the value that is calculated by the function. Same thing, as you can see, right? Degrees of freedom is 2, 3 minus 1, 3 categories minus 1, and the p-value 0.061. It's the same as what we compared earlier. Okay, so all the steps that we did, they could be pretty much packaged in one line by calling this function chi-squared.test. Okay, so that's it. That's the end of this lecture, and the homework will be posted for this problem, for this topic as well.